All right, so next we want to move on to Monte Carlo simulations, which are not a simulation methodology so much as I'm sorry, not a simulation type as in like agent-based modeling or discrete event system simulation or system dynamics modeling, but more of a methodology that could be applied to kind of all other simulation methodologies. But the key feature behind Monte Carlo simulations, which you'll get a lot of chance to experiment with in Lab 3, is that they are static. So we don't we can you can run a Monte Carlo simulation on a dynamic simulation, a simulation which simulates things how they change over time, but you end up sampling it like right at the end of the simulation. So you sort of see that even though you might care about the dynamics in some other world, in this case you only care about where things end. So every Monte Carlo run or trial results in a single, possibly multivariate. So you can measure multiple things, but they all kind of are paired together. So we're taking the measurements at the end of an experiment, and that's why you can liken it to a game of chance. So let's say you pull the handle on a slot machine, or you roll a roulette wheel or something along those lines. Those are all things where you trigger the thing to go on, and at the end you see where things stand, and that's the result of the experiment or the sample. So because you're only running one, we can't really tell a lot. But if we run a lot of them over and over again, then we get a distribution of outcomes, and that distribution of outcomes ends up being where we can end up getting the real inferential power. So running multiple experiments helps us gain statistical power. All right. And by the way, the term Monte Carlo comes actually sort of strangely enough from the building and the design of the atomic bomb, the first atomic bomb. So the mathematicians who were working on simulation frameworks to try to predict parameters that were used in the design of the bomb uh, were coming up with these methods of Monte Carlo sampling, and they I think internally probably used something called like random sampling or a term like that, but then externally, because it was highly top secret, they didn't really have a way to refer to what they were doing, and so they just referred them as the Monte Carlo method. And Monte Carlo being that casino, sort of famous casino, and they were thinking, well, these are games of chance, so that relates to a casino, so we're going to call it Monte Carlo, and that's their kind of cute name behind it. And now, even though this method is well known, outside of these military applications, used in huge numbers of applications, we still use this funny name, the Monte Carlo method. So that's where that comes from. All right, so an example here. So if you look in your textbook, there's this reliability problem with a milling machine that each has three ball bearings. Now, each ball bearing can fail independently, but every time you replace a single ball bearing, you have to take the machine down. It's costly in terms of the downtime of the machine, but it's also costly in terms of the ball bearings you have to buy and the labor you have to pay for of the guy or gal who's replacing the ball bearings. So the question is, can we adjust the replacement schedule to kind of optimize operational costs, and how should we do that? So you could imagine different schedules. So if a ball bearing's lifetime is drawn randomly, and we want to calculate the cost of 45 ball bearing replacements, we could have these different ways to so you can sort of think about it. Well, I'm going to replace 45 ball bearings, and so I'm effectively paying the cost of replacing 45 ball bearings. So I could either replace every time a single ball bearing fails, I could just replace all three ball bearings. And that way I don't have to worry about taking the machine down a short time after that, because another ball bearing is probably likely to fail. So even though I'm wasting the life on the good ball bearings that I'm replacing, I could just still replace all of them, because I don't want to pay so much labor cost, nor do I want to take the machine down for this long amount of time. So I don't like the machine downtime, and so I'm just going to replace everything. Alternatively, you could flip that around and say, well, I actually don't like the idea of having these two other ball bearings that aren't getting their full lifetime, and so I am going to just replace them one at a time. That way I'm sure to get the full lifetime of all the ball bearings out. realizing that those ball bearings, that the extra downtime you're going to have to pay in the machine time in order to replace those ball bearings when they fail may end up affecting the productivity of the machine. So that may actually be, or just actually may be much more labor costly. So you may have to pay a lot more labor. So there's a benefit to replacing all the ball bearings at once, even though you've got extra lifetime out of some of those ball bearings. But there's also a cost, because again, that's extra lifetime. You could have gotten all those ball bearings. And now the book doesn't consider it, but you could also imagine some regular schedule where maybe every year you replace all 3 ball bearings, regardless of whether one failed. So you could imagine comparing all of those. So we think the accumulated downtime and labor costs might be greater than the gains from operating their ball bearings for full lifetimes, and we would like to use a simulation to show that. So our prediction is that after we run our simulation, we'll see that if all bearings are replaced at the same time, then the total accumulated cost will be less than the one if each ball bearing is replaced as it fails. So the accumulated cost, that's in terms of our downtime of the machine and even our labor costs, but I'll mainly sort of talk about the downtime here. So that's what we want to test with simulation. We might be wrong. That's the whole point of the simulation, to see if we're wrong. So how do we do this? Well, in a spreadsheet, we basically create 45 rows. Each row is going to have 3 times in it. A time for the failure of ball bearing 1, ball bearing 2, and ball bearing 3. I'm sorry, I said 45 rows, I meant 15 rows. 15 times 3 is 45. So we look at each one of these and we say, all right, so the Monte Carlo lifetime is sample is going to be the lifetime and delay accumulated from those 15 rows. So one row is the failure times for 3 ball bearings that were installed at the same time. And so if you got 15 rows, that's where you get your 45 ball bearings. So then we can end up generating these cost distributions. So what I mean by that is, let's say you look at these 3 ball bearing pairs. If we replace them all separately, then we know that we're going to get the full lifetime, so all of the machine lifetime out of those 3 ball bearings. But we're going to have to pay for the downtime and labor costs for 3 separate times. But in the other schedule, we'll only get the minimum of those 3 ball bearings out of their lifetime, but we'll only have to pay the cost once. So those are the 2 differences between that. So every row, you've got 3 ball bearing times, and in the 2 policies, you either get the machine running time is either going to be the minimum time until failure of one of those ball bearings, or it'll be the accumulated time across all of the ball bearings. But in the latter case, where it's the accumulated time, you have to pay the labor cost more often. Whereas in the time where you take the minimum of the ball bearings, you only have to pay the labor cost once. Yeah. So that's basically the difference there, where you're generating these failure times and then figuring out these 2 different alternatives. So the one question is, how many samples do we need to generate cost distributions, and is one run enough for each schedule? So one run is probably not enough for us to so you might just run a So the Monte Carlo sample is from the 15 rows, and so one run is from all 15 rows. 2 runs would be me running this twice, so I'd have 15 rows and another 15 rows. 3 runs would be 15 rows, another 15 rows, another 15 rows, and so for each one I've got a performance distribution. And so the question is, how many of those chunks of 15 do I need in order for me to generate any confidence in the cost distributions that I get out? So if I run just 15, that might not be enough. But in this case, because the performance measure that I'm getting out is actually the sum over all of these 15 rows, then I might have very, very low variance in that 15 row chunk. And I might not need to run many of these. It might be enough for me to just run this experiment once with just those 15 rows. So, but that ends up being the balance that we'll talk about as we get towards the second half of the class, is how the variance in our simulation determines how many instances of the simulation we need to run in order to be confident in our results. Now that might be a little bit murky, but again, I encourage you to be reading the book and to check out how the book was implemented and see what their results ended up looking like. All right, so the other Monte Carlo case that I wanted to give, it's similar to our Lab 3 activity for estimating pi, is this question that we have, say, a bomber, and they end up dropping, they only can drop 10 bombs on an area. And when you drop a bomb, it doesn't land right exactly on a target. It falls according to some statistical distribution. So the question is, given that each bomb has a particular statistical distribution, then we want to know sort of what is the number of bombs in a mission that reach a given target area. So if you drop a bunch of bombs over an area and the target area is a small subset of that area and the bombs could land anywhere in their kind of distribution of possibilities, then how many actually land where we want them to land? How can we do that in Excel? So a 10 bomb mission run can be implemented in one spreadsheet row where we generate 10 pairs of coordinates x and y. So you generate a random x coordinate, from like 0 to however, your maximum x coordinate is. You generate a y coordinate from 0 to your maximum y coordinate, and then that pair is where that one bomb landed. And you can do that 10 times. And so each MC run, then you can then say, based on those 10 XY pairs, I can then ask how many of those pairs actually landed inside the area of interest. And so at the very end of that row, you have like a count from 0 to 10, which tells you how many bombs landed in your target. So then you can run that, take that row and fill that down for hundreds of rows, and you get hundreds of MC run samples. And then you can take a distribution of that number, and you can say how many of what is the distribution of numbers of bombs that land in the area. And so again, the question is how many runs are enough in order to feel confident in this distribution. And again, that's going to vary with how variable the outputs are. And so we can't know that ahead of time without running a few trial experiments to get an idea of what the variance is, and then using that variance to then predict roughly how many more do we have to run to get some level of confidence, which again is something we handle in kind of the second half of the class. All right, so we've gone over a couple of those examples. There's another example in the book, this estimating lead time demand example. I'm not going to go over in any detail here, but if you need another example of these kind of Monte Carlo things, I encourage you to take a look. Section 253. I do want to spend a little bit of time on another example that you'll see in Lab 3, this stochastic activity network. And so the idea is you have a network of activities and you're trying to figure out how long it'll take to complete all of the activities. And so take an example for, say there's a breakfast example where you have all three of these things need to be done in order for breakfast to be served. Eggs must be made, but let's say to make eggs you have 3 randomly timed steps, and that might involve getting the eggs out, cracking the eggs, it might involve mixing the eggs, it might involve actually then making the scrambled eggs or whatever type of eggs you're doing. So there might be 3 steps that have to follow in sequence that happen, that each one have a random time. But while you're making eggs, someone else could be making toast. Now toast might have 2 randomly timed steps. You need to actually make the toast, and then you actually have to put something on the toast, for example. And that could be going on in parallel with the eggs. Toast might finish before the eggs, or the eggs might finish before the toast. And any given breakfast, one might finish first, and then the other one might finish first the other breakfast. And then you might have another activity, let's say, I don't know, making bacon, and that might have just one single randomly timed step, but it just takes, a long amount of time, and that's going on at the same time of these. And the question is, so you need all three, and so the duration of breakfast preparation is going to be whichever one of these three takes the longest. Now, if I make an activity network like the one below, then the top branch are all three steps of making the eggs. So this is a uniformly distributed time between, say, 2 minutes and 4 minutes. This is a uniformly distributed time between 2 minutes and 4 minutes. And this is a uniformly distributed time between 2 minutes and 4 minutes. The average time for this branch is 3 minutes, 3 minutes, and 3 minutes. So if I add up across these whole branches, I get an average time of 9 minutes. On this branch, we have a uniform distributed time between 3 and 6, and another uniform distributed time between 3 and 6. They have to happen in this sequence. So this has an average time of 4.5 minutes, right in the middle, 6 plus 3 divided by 2. This also has an average time of 4.5 minutes. So the average time of this branch is also 9 minutes. This branch is a single random number uniformly distributed between 6 and 12. Its average is going to be 9 minutes, and that's just 12 plus 6 divided by 2. 12, 6, 18 divided by 2, 9. So 9 minutes. So all three branches have a mean duration of 9 minutes. And so you might imagine that if we asked for any given breakfast, which one ends first, might just be picking uniformly between the three of them. So in other words, there's no reason to believe that one would take longer, would more often be longer than another because they all have the same average time. But again, part of the reason we use simulations is that averages sometimes can be deceiving, and this will be one of those cases where the averages will be deceiving, and it turns out that the fact that you've broken this up into multiple parts is going to affect whether it is more likely or less likely to take a longer time than one big part. So that's what you'll explore in the lab. And the way that'll work, and the lab TA will go over this as well, is that in each spreadsheet row, you store those 6 numbers. I'll go back. See, 1, 2, 3, 4, 5, 6 random numbers. Every breakfast is modeled by 6 random numbers, 3 U24 numbers, 2 U36 numbers, and 1 U612 number. So in every spreadsheet row, it represents a breakfast, and so you draw 6 numbers. And those 6 numbers are going to have the 3 from the top branch, the 2 from the middle branch, and the 1 from the bottom branch. And so at the end of that row, you can then say, how long did breakfast take? Well, you can calculate the length of the first branch, the top branch, the length of the middle branch, and the length of the bottom branch, and you can simply ask which one's longer. And whichever one is longer, that's the length of the breakfast. That is how long it took to make the breakfast. And then you also can ask, once you know which one's longer, which path, 1, 2, or 3, so 1 being the top, 2 being the middle, 3 being the bottom, which of those 3 paths is the one that is the so-called critical path? Which one took the longest? And can I get a distribution of these so-called critical paths? In other words, how often is 1 the critical path, 2 the critical path, and 3 the critical path? If you assume that it doesn't matter, then they'd be equally have equal frequencies, 1, 2, and 3. But if it does matter, then 1 might be greater than 2, 2 might be greater than 3, or some other patterning. So that's what you'll be exploring in the lab. Now, you're going to run hundreds or thousands of these simulated breakfasts in order to figure out whether you've got the right distribution. And so the question is, again, how many runs are enough, which is, again, something which we will handle in the second part of the course. But basically, you can notice as you run more and more of these runs, you should start getting more and more stable distributions. And that kind of gives you an idea that there's some like diminishing marginal utility to running more and more runs, that eventually the benefit you get from running another 10 more runs just simply doesn't make up for the cost of the time it takes to run 10 more runs. All right, so we're going to pause here. Go back to Canvas, look at the question set there, and then we're going to do a quick wrap up, bringing things back to DES.